When you are new to security architecture, it is easy to assume that static analysis is a kind of security magic because it can scan code quickly and report problems you would never notice by reading files one by one. That excitement often fades the first time you see a results list that feels endless, filled with warnings that may not be real risks or may not matter in your specific system. This is where many teams either give up or they keep the tool running but stop paying attention, which is almost worse because it creates a comforting illusion of safety. Static analysis can absolutely improve security, but only when you treat it as a disciplined practice that is shaped by your architecture goals and your threat model, not as a scoreboard of how many alerts you can generate. The central challenge is avoiding false positives and low-value findings while still catching the high-impact weaknesses that are easiest to fix early. In this episode, we focus on how to use static analysis effectively, how to interpret results through an architectural lens, and how to build a workflow that keeps signal high and noise manageable without drifting into resignation. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Static analysis means examining code and related artifacts without executing them, looking for patterns that suggest vulnerabilities, risky behaviors, or violations of secure coding rules. A key advantage is that it can be done early, even before a system is deployed, which makes it a natural partner to architecture work that aims to prevent weaknesses rather than react to incidents. Another advantage is consistency, because the same checks can be applied across many code bases and many changes, which is valuable in environments where systems evolve constantly. The limitation, and the source of frustration, is that static analysis is forced to infer meaning from code structure, so it sometimes flags safe patterns as risky and misses risky behavior that depends on runtime state. It also struggles with business logic flaws, such as improper approval workflows, because those flaws are about intent, not just syntax. For beginners, the most important mindset shift is to stop treating static analysis as a judge that declares secure or insecure and start treating it as a sensor that produces hypotheses. Your job is to decide which hypotheses matter, which ones are false, and which ones indicate deeper architectural gaps, such as inconsistent authorization or unsafe data handling. A common starting point for static analysis is static application security testing, SAST, which focuses on identifying common classes of coding weaknesses, such as injection risks, insecure cryptographic usage, and unsafe input handling. The first time you mention it, it is helpful to remember that SAST is not a guarantee that an issue can be exploited, only that code patterns resemble known risk patterns. When used well, SAST can prevent entire categories of vulnerabilities from ever reaching production, especially in code paths that are exposed to untrusted inputs. When used poorly, it can become a fire hose of warnings that overwhelms developers and pushes them into ignoring security. The way to avoid that outcome is to connect SAST to your architecture's trust boundaries and critical workflows. If your architecture relies on strict input validation at a boundary, then SAST findings about input handling near that boundary are high value. If your architecture relies on safe data handling for regulated data, then findings about data exposure and logging become high value. The tool is not the strategy, and the strategy must be rooted in what your design is trying to protect. False positives happen for several reasons, and understanding those reasons helps you manage them without becoming cynical. Static analysis often lacks full context about how data is used, such as whether an input is already validated upstream or whether a function is reachable by untrusted users. It can also misunderstand frameworks, libraries, and patterns that generate code dynamically or that handle security in a centralized way. Sometimes it flags a risk because it sees user input flowing to a sensitive function, but the code includes a safe transformation or strict validation that the tool cannot confidently recognize. Other times the tool flags a risk because a function could be misused, even if your architecture prevents that misuse through access control and segmentation. This does not mean the warnings are useless. It means they require triage. The goal is not to eliminate false positives completely, because that is unrealistic, but to keep them from stealing attention from the findings that indicate real, reachable risk. The best teams treat false positives as a calibration problem, adjusting rules and workflows until the tool matches the system's reality. When you make calibration part of the plan, static analysis becomes less frustrating and more reliable. To avoid drowning, you need a triage approach that begins with risk-based prioritization instead of volume-based panic. Risk-based triage asks where the finding sits relative to your highest value assets and most exposed trust boundaries. For example, a potential injection warning in a public-facing request handler is more urgent than a similar warning in a low-privilege internal helper function that cannot be reached by untrusted inputs. A warning about hard-coded secrets or insecure credential handling is high priority because it can undermine multiple controls at once, especially if it affects authentication or service-to-service trust. A warning about weak authorization checks is also high priority because authorization failures often lead directly to data exposure or privilege escalation. Meanwhile, many style-based warnings or low-impact error handling warnings may be less urgent, even if they are technically correct. This is not about ignoring problems. It is about sequencing effort so that the architecture's most important promises are protected first. A beginner-friendly rule is to prioritize findings that affect identity, privilege, sensitive data flows, and boundary enforcement, because those categories align with the most common high-impact incidents. When triage follows architecture priorities, the work stays focused. It also helps to classify static findings by whether they represent a local coding issue or a systemic pattern problem, because the best fix is different in each case. A local issue might be a specific unsafe function call or a missing validation step in one file, which can often be fixed directly. A systemic pattern problem appears when many findings share a theme, such as inconsistent input validation, scattered authorization checks, or repeated risky cryptographic usage. Systemic issues suggest that the architecture lacks a standard enforcement point or a shared pattern, so developers implement security inconsistently across the codebase. In that situation, fixing individual findings one by one can feel endless because the system keeps generating the same mistakes. A better approach is to adjust the design by defining a central policy enforcement pattern, creating shared libraries, or enforcing consistent boundaries so the vulnerable pattern becomes harder to write. Static analysis is valuable here because it reveals repetition, and repetition is often evidence of an architectural gap. For beginners, learning to recognize when a finding is a symptom rather than a cause is a major step forward. When you respond to patterns with architecture improvements, you reduce future noise and increase security at the same time. Managing false positives is not only about triage, but also about tuning and scoping, because static analysis tools are most useful when they are aligned to the code you actually care about. Scoping means deciding which repositories, modules, and languages should be scanned first, based on exposure and criticality. A large system may include test code, prototypes, and legacy modules that are not deployed, and scanning everything equally can create noise that hides real risk. Tuning means adjusting rule sets so that checks match your environment, your frameworks, and your security standards. For example, you might tune rules to recognize your approved input validation patterns, so the tool does not repeatedly flag safe code. You might also tune rules to elevate certain categories, like secrets handling, because even a small number of those findings can represent a serious architectural breakdown. Tuning is not cheating. It is how you turn a generic tool into a useful instrument for your specific system. The goal is to avoid both extremes of turning everything on and turning everything off. A tuned, scoped approach produces a manageable stream of findings that teams can act on consistently. Another powerful way to reduce false positives is to integrate architectural context into how findings are interpreted, especially by mapping reachability and trust boundaries. Reachability means whether a vulnerable path can actually be triggered by an attacker, given how the system is exposed and how access control is enforced. Trust boundaries define where untrusted input is allowed to enter and where identity and authorization must be verified. If a static finding points to a risky function, you ask whether that function is behind authentication, whether authorization is enforced before it is called, and whether the input comes from an untrusted source. This does not excuse risky code, but but it helps you prioritize and choose the right mitigation. Sometimes the best mitigation is to fix the code, and sometimes the best mitigation is to move enforcement earlier in the flow, such as adding a boundary validation step that makes multiple code paths safer. Architecture context also helps you decide whether a warning should be tracked as an architectural gap rather than as a bug. For example, many authorization-related warnings may indicate that authorization logic is scattered and inconsistent, which is an architecture quality issue. When you use context deliberately, static analysis becomes a tool for design improvement, not just bug hunting. Static analysis can also be used effectively by linking it to secure coding standards and definition of done expectations, because this changes how teams perceive findings. If security is treated as optional cleanup, findings pile up and become political, with developers feeling blamed for backlog they cannot control. If security is treated as part of normal quality, then static analysis results become routine signals that guide improvements. This is where architectural leadership matters, because architecture sets expectations about where controls should exist and how they should be implemented. For example, if the design mandates centralized authorization enforcement, the definition of done can include passing relevant static checks that confirm authorization patterns are used consistently. If the design mandates safe secrets handling, the definition of done can include zero tolerance for hard-coded secrets warnings. The point is not to punish developers, but to create clear boundaries about what is acceptable in the codebase. When expectations are clear, static analysis is less about debate and more about meeting shared standards. This is one of the best ways to prevent drowning, because the work becomes continuous instead of accumulating as a crisis. One subtle reason static analysis becomes overwhelming is that teams treat findings as a single undifferentiated pile rather than separating immediate risks from long-term hygiene. Some findings represent urgent exposure, such as a path that allows injection or a misused cryptographic function in an authentication flow. Other findings represent code quality issues that could become security problems later, such as error handling that reveals too much context or input checks that are inconsistent but not currently exploitable. Both categories matter, but they should be handled differently. Urgent findings should be addressed quickly because they can affect current risk. Hygiene findings should be planned and improved through patterns, refactoring, and shared components so the codebase becomes safer over time. If you treat all findings as urgent, you create burnout and resentment. If you treat all findings as optional, you create drift and a growing risk surface. A balanced approach keeps the signal strong and the process sustainable, which is exactly what beginners need to learn early. Sustainable security is not about ignoring the long tail, but about handling it in a planned way. Static analysis is most effective when it works alongside other methods, because each method covers different blind spots. Dynamic analysis can reveal runtime-only issues like state confusion and misconfiguration effects, while manual review can reveal business logic flaws and workflow bypasses. Static analysis, by contrast, is excellent at catching insecure patterns repeatedly across a codebase and at preventing known classes of mistakes from spreading. When you combine methods, you can confirm whether static findings represent real exploit paths and whether fixes actually reduce risk at runtime. This combination also reduces false positives because dynamic observations can validate whether a flagged path is reachable and whether the risky behavior actually occurs. At the architecture level, this integrated approach supports traceability, where you can map a threat to a requirement to a design decision, and a design decision to evidence from analysis and testing. For beginners, the most important lesson is that static analysis is not a standalone proof, but a reliable contributor to a larger validation story. When you expect it to be a contributor rather than a verdict, you interpret findings more calmly and productively. That calmness is what keeps teams from drowning. Another practical technique for avoiding overwhelm is to focus on incremental improvement, especially by using baselines that prevent old debt from blocking new progress. Many real systems already contain large numbers of legacy findings, and insisting that everything be fixed immediately can stop development or cause teams to disable the tool. A better approach is to establish a baseline, meaning you record the current state and then require that new changes do not introduce additional high-severity findings. Over time, The baseline shrinks as teams fix issues during normal work, but progress remains possible without an impossible initial cleanup. This is not lowering standards. It is choosing a realistic path to higher standards. Architecture can help by identifying which modules are most critical and should be cleaned first, and which findings represent systemic pattern problems that require architectural refactoring. A baseline approach also encourages developers to learn from findings as they work, because each new change is a chance to improve rather than a chance to inherit an overwhelming backlog. For beginners, this illustrates a key principle of secure architecture. The goal is durable improvement, not heroic one-time cleanups. It is also important to think about how static analysis findings are communicated, because communication affects whether results lead to better design or to defensive behavior. Findings should be presented in a way that ties them to system behavior and impact, not just to rule identifiers. If a finding indicates a potential injection path, explain what input is involved, what sensitive operation is at risk, and what boundary should enforce validation. If a finding indicates insecure randomness or weak cryptographic usage, explain what security property could fail, such as confidentiality or integrity of tokens. If a finding indicates missing authorization checks, explain what unauthorized action could occur and which roles would be affected. This kind of communication turns alerts into learning moments and helps teams decide whether the fix should be local or architectural. It also helps beginners build intuition about which categories of findings are truly dangerous and why. When communication is vague, people argue about whether the tool is right. When communication is clear, people focus on how to improve the design. Clear communication is a non-technical control that dramatically increases the value of technical tools. As you become more confident, you can use static analysis not only to catch mistakes, but to enforce architectural patterns, which is one of its highest value uses. If your architecture requires that all sensitive data access goes through a specific authorization and filtering layer, static checks can help detect when code bypasses that layer. If your architecture requires consistent input validation at trust boundaries, static checks can detect when boundary handlers accept raw input without validation. If your architecture requires secure secrets handling patterns, static checks can detect when secrets are embedded or logged unsafely. This turns static analysis into a form of guardrail that keeps the design from drifting as the system evolves. Guardrails matter because drift is one of the biggest long-term threats to security, and drift often happens quietly through small changes. When static analysis is aligned to architecture patterns, it becomes a way to keep promises over time. For beginners, this is a powerful insight. The tool becomes more valuable when it is attached to your design philosophy, not when it is used as a generic scanner. That alignment is what keeps the signal strong and the noise manageable. By the end of this discussion, the main message should feel practical rather than intimidating, because static analysis is most effective when you approach it with steady, structured habits. You use approaches like SAST to catch repeated insecure patterns early, but you refuse to be ruled by raw alert counts, because those counts do not reflect real risk. You triage findings based on architecture priorities like trust boundaries, identity and privilege, and sensitive data flows, and you distinguish local bugs from systemic pattern problems that require design improvements. You tune and scope the tool so it matches your environment and frameworks, and you interpret findings with reachability and boundary context so false positives do not steal attention from high-impact issues. You integrate static analysis with dynamic testing and manual review so evidence is balanced and confidence is stronger, and you use baselines and incremental improvement to keep the workflow sustainable. Most importantly, you treat static analysis findings as inputs to clearer requirements and stronger patterns, which is how you prevent drowning and turn scanning into real security progress. When you can do that consistently, static analysis stops being a noisy burden and becomes a dependable part of architecture quality.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.